Welcome to this tutorial in reinforced concrete design. In this tutorial, we will be solving a doubly reinforced section after we go through a quick recap of the procedure. So before we get into the worked examples, just a quick recap. The full theory, derivations, and the background on doubly reinforced beams is covered in the lectures. Here we're only revisiting the essential ideas needed for the tutorial. Although our default in design is to use singly reinforced sections, there are situations when the concrete alone cannot provide enough compression resistance. This often happens when the overall depth of the beam is restricted. For example, if we have headroom limitations, architectural constraints, or existing geometry. In those cases, we introduce compression steel so that part of the compression is carried by reinforcement rather than concrete. It's also worth remembering that any beam with structural importance will have reinforcement at both the top and the bottom. You must always provide a minimum amount of steel in the compression zone. In doubly reinforced design, that compression steel becomes an active part of the section's capacity when the concrete alone can't provide enough resistance. This slide gives a quick recap of the key ideas behind doubly reinforced rectangular sections. The Eurocode does not provide explicit design formulas for this case, but the approach we use is valid for the concrete and steel grades listed here. In a singly reinforced section, there is a limit to how much compressive force the concrete can provide, and that maximum concrete compression is CSR, for singly reinforced, equals KBD FCK, and therefore the corresponding limiting moment is MSR equals KBD squared FCK. As long as the design moment is below this value, the section can be designed using tension steel only. However, once the applied moment exceeds MSR, the concrete cannot provide any additional compression beyond CSR. At that point, extra compressive force must be carried by reinforcement in the compression zone. That is the essence of a doubly reinforced section. The compression steel provides the additional force needed to balance the larger design moment. This slide introduces the additional compression force provided by the compression steel. Once the concrete has reached its maximum compressive capacity, CSR, any extra compression needed to balance the design moment must come from the reinforcement in the compression zone, and that contribution is CSC equals AS tag FS tag, where AS tag is the area of compression steel and FS tag is the stress it develops under bending. The compression steel acts at a lever arm measured from the tension steel, and that distance, ZSC, is D minus D tag. This lever arm is slightly shorter than the tension lever arm because the compression steel is closer to the top of the section. Finally, note that in these simplified equations, we ignore the small reduction in concrete area, which is caused by placing the compression bars. For normal reinforcement ratios, this has a negligible effect on the strength. Here we can see how we determine the stress developed in the compression steel. Because the section is in bending, the strain profile is assumed to remain linear across the depth, and that means that the strain in compression steel is simply the concrete strain at that level. Using similar triangles, the strain in the compression steel, epsilon SC, is epsilon Cu, the maximum strain in concrete, times x minus d tag over x. This depends on how far the compression steel sits below the neutral axis. As long as the compression steel has not yet yielded, its stress will follow Hooke's law. So Fs tag, the stress in the steel, equals Es, the modulus of elasticity, times epsilon Sc. This is shown in the bilinear stress-strain diagram. The steel behaves elastically up to the yield strain, after which the stress remains approximately constant. This relationship is key in doubly reinforced design because the amount of compression carried by the steel depends on whether it is still elastic or reached yield. We can check if the compression steel actually reaches yield. In compression, steel yields at a stress of 0.87 FYK, and the corresponding yield strain is epsilon yield, which is 0.87 FYK over ES. For typical values of FYK equals 500 megapascals and ES equals 200 gigapascals, this gives a yield strain of about 0.0022. We can then compare this strain with the strain in the compression steel from the linear strain profile that we discussed. Epsilon SC equals epsilon Cu3 x minus d tag over x. So the compression steel will yield if that strain is at least 0.0022. Whether that happens depends on the position of the steel relative to the neutral axis. And we'll see exactly how to calculate this condition when we work through the example. And finally, we can bring together the moment equilibrium for a doubly reinforced section. When we take moments around the tension steel, the total moment resistance comes from two parts. The concrete compression block, CSR, acting at its lever arm of ZU, and the compression steel, CSC, acting at its lever arm, ZSC. Adding these gives the moment around the tension force to be CSR times ZU plus CSC times ZSC. Rearranging this expression allows us to calculate the required area of compression steel. The required area of the compression steel is the design moment minus the moment that the section can carry as a singly reinforced beam divided by the strength of steel times D minus D tag. This shows that the compression steel is only needed to carry the excess moment beyond what the concrete can resist alone. For equilibrium, the tensile force in the reinforcement must equal the total compressive force. So T, which is AS times 0.87 FYK, must equal CSR plus CSC. So once AS tag is known, we can determine the additional tension steel required. Finally, it's important to remember that compression bars must be properly restrained to prevent them from buckling under compression. In practice, this is achieved by tying them to the links. And now, we're ready to solve an example. So here in this example, we have an 8-meter simply supported span carrying both permanent and variable loads. This gives us a uniformly distributed design load to work with. The section is 200 millimeters wide with an effective depth of 360 millimeters. The compression steel is located at 50 millimeters from the top. With the material strengths given, our task is to design the reinforcement at mid-span where the bending moment is the greatest. In this example, we'll work step by step through the moment capacity of the concrete, check if the section needs compression steel, and then determine both the compression and tension reinforcement required. And these are the steps we'll follow to work through the example. First, we determine the design moment at mid-span from the applied loading. Then we compare that with the maximum moment the section can carry as a singly reinforced beam. This tells us immediately whether compression steel is required. If it is, we size the compression reinforcement first, because it balances the excess moment beyond the concrete's capacity. Once that is known, we can complete the design by determining the required tension reinforcement. And finally, we can carry out the standard reinforcement checks to ensure the section satisfies all code requirements. So let's start with a solution of this doubly reinforced beam. You can see here that I'm doing it on calculation sheets where you have on the left-hand side the reference. So where from the Eurocode, for example, have you taken the equations from, in the middle of the calculations, and any output that we're taking forward on the right-hand side. So here I've just put all the input that we already went over into the sheet. And we'll start now by finding the design load and ultimate moment. So the ultimate design load at the serviceability state is W, which equals to the safety factor for permanent loads, which is 1.35, times the permanent load, which was given as 10, plus 1.5, which is the partial safety factor for variable loads, times the variable load, 6. And that gives us a UDL of 22.5 kilonewtons per meter. Now, this is a simply supported beam, so obviously the moment will happen in the middle, and the maximum moment of a simply supported beam under UDL is WL squared over 8. So in our case, it is 22.5 times 8 squared over 8, and that gives us a design moment of 180 kilonewton meters. So this is the moment that the section has to resist. Let's now look at the reinforcement requirement. The first thing that I'm going to do in this case is check how much moment the beam can resist as a singly reinforced section. And to do that, I'm going to use the limiting K of 0.168 as per UK recommendation. So remember, as long as K is under 0.168, we can design a singly reinforced beam. I am here checking the limit. So you can see here that if I substitute K with 0.168, I will get the moment that the section can carry as a singly reinforced beam, which will work out as 0.168 times B, which is given as 200 millimeters, times D squared, which we know is 360 millimeters, and times FCK, which is 25, as per the example. I need to multiply by K to the minus 6 to organize my units because my concrete strength is given in megapascals, so that is newtons over millimeters squared, and I want my moment in kilonewton meters. That makes it much easier to compare to what I already have. And this moment works out as 108.9 kilonewton meters. Now here we can see that the moment that my section has to carry, so MED, the design moment that we found on the previous slide, is bigger than what the section can carry as a singly reinforced beam. That means I have to bridge that gap with compression steel. I can find Z, so just like we've done before, d over 2 times 1 plus a square root of 1 minus 3.53k, and that gives me 295 millimeters. Now I do need to check if that is under 0.95d, which it is in this case, and then I can move on to finding x. X is 2.5 times d minus z. D I know from the question, that is 360, and I've just found z as 295, and I get that x is 163 millimeters. Now that I know that I need compression reinforcement, the first thing that I need to do is check the strain in the compression steel. So if you remember from before, the strain in the compression steel is the maximum strain in the concrete, 0.0035, times X, which I just found to be 163, minus D tag, which I know is 50 because that was given, and that works out as 0.0024. Now that is bigger than the yield strain in steel, which we've already discussed is 0.0022. And that means that the steel has already yielded. Therefore, if we look at the bilinear curve, we are already in the yield stage, and Fs, the stress in the compression steel, is 0.87 FYK. And therefore, the required compression steel is the design moment minus the moment that the section can carry as a singly reinforced beam. So that's the gap that we need to bridge with compression steel, divided by the strength in steel, which we've just found is 0.87 times 500, and all that times by D minus D tag, which is 360 minus 50. Once again, I need to organize my units here, so I have to multiply by 10 to the power of 6. And I get that the required area of steel in the compression reinforcement is 528 millimeters square. Now, if we take bars of 12 millimeters, for example, I can find out how many bars I need by taking the whole area of steel that I need to provide and dividing it with the area of 1 bar, which is pi times the diameter squared over 4. And that gives me 4.7. Obviously, I always need to provide more reinforcement rather than less, and I need to provide 5 bars. And if I have 5, I can figure out exactly what compression steel is provided. So 5 times the area of 1 beam of 12, the actual steel area that I'm providing here in compression, which works out to be 565 millimeters square. And now that we know the compression reinforcement, we can calculate the tensile reinforcement. And that is going to be what the concrete can carry by itself, which is the limit of the moment of the singly reinforced section, just as we would have calculated for a singly reinforced beam, plus the area of steel provided in compression. So we know that the moment that the section can carry as a singly reinforced beam is 108.9, and that gets divided by 0.87 times the strength of steel, 500, times Z, which we found to be 295, and we have to add on to that the area of steel that is required, not provided. And that works out as 1,376 millimeters square. In this case, I'm going to take bars of 22 millimeters. We can figure out how many bars. It works out to be 3.6, so we take 4 bars. And that means that the area we're providing in tension is 4 times the area of 1 bar of 22. And that works out as 1,521 millimeters square. So at this point, we have both the required areas of compression and tension steel, and also the actual steel that we're providing in both these cases. Now, the last thing we want to do is just some reinforcement checks. Obviously, there are other checks like the spacing of bars and things like that that we won't get into now, but we want to just look at the maximum and minimum areas that we've provided. So here we've provided 1,521 millimeters square in tension, and we've provided 565 millimeters square in compression. And if we look at these equations that we've discussed in the lectures for minimum reinforcement and for maximum reinforcement, we can see that the minimum reinforcement required is 97 millimeters squared, and the maximum is 2,880. And we check each of our areas that we provided, both the tension and both the compression, and we can see that they are within the range between the minimum and maximum. And that's it. That's the beam solved. However, before we finish, let's explore how the doubly reinforced design responds to a change in the compression steel position. Everything else in the beam remains the same as in example 1. The only difference is that the compression steel is now placed at an inset of DTAG of 70mm instead of 50mm. Our aim here is to see how this affects the required reinforcement. By increasing DTAG, we reduce the lever arm for the compression steel, and that has a direct impact on the amount of compression steel and tension steel needed. We'll use exactly the same steps and equations as before, but with this new value, DTAG, to see how the design adjusts. So here we can see once again the input. I've taken all the input that we've had before, only changing the inset from 50 to 70. And we can see here that I've also added the design moment and the moment that the section can carry as a singly reinforced beam, because those do not change. They're not dependent on the inset. The same goes for the values of Z and X. They do not depend on DTAG, so I've just left them the same and taken them from the previous example. So, as we said before, design load and ultimate moment, we've already calculated, that does not change. The compression reinforcement, however, does change. The first thing we do, once again, is we will check the strain in the compression steel. The only change here is that we have the 70 instead of the 50 we had before, but that reduces the strain in the compression steel to 0.00199. Now that is smaller than the yield strain in steel of 0.0022. And that means that the compression steel hasn't yielded, and therefore the stress in the compression steel is along the linear line going up to yield, which gives us a value of the modulus of elasticity of steel, ES, times the actual strain that we've just found. So in this case, 200 gigapascals times 0.00199, and that gives us a strength of compression steel of 398 megapascals. These two things, DTAG and FS tag, obviously change the required steel in the compression zone. The top bit, the MED minus MSR, does not change, that stays the same. However, at the bottom we have 398, the stress in the steel, times 360 minus 70. And that gives us a new required area of steel in the compression zone of 616 millimeters square. If we take 6 bars of 12 in this example, we'll be able to provide 679 millimeters square of reinforcement. Now this obviously also influences the tensile reinforcement. So the required area of steel, that first bit doesn't change, MSR divided by 0.87 FYK times Z. However, AS tag required has changed, and that brings a different area required for the tensile reinforcement. In this case, 1,464 millimeters square. We can see that if we provide 4 bars of 22, we end up actually in this case with the same area for the tension reinforcement. And that is because the change wasn't really significant enough to bring any real change to the tensile reinforcement. And that's it, back to the same checks as before. The area for AS min and AS max does not change, and we can see here that the provided areas of steel, both for tension reinforcement and compression reinforcement, are in between those two limits. And that's this example finished. And that's it. We've solved a double example of a doubly reinforced beam. I hope that was helpful, especially seeing how the inset can change the area of reinforcement for compression and also influence if the steel has yielded or not. Hope to see you next time for some more reinforced concrete design.